Hello again. Now we are in lecture 15, first part. In this video, we are going to consider now non-homogeneous non-homogeneous linear equations with constant coefficients. And to solve such equations, first we are going to consider method of undetermined coefficients. Okay, first a few words for general non-homogeneous equations. We consider equations of the form. So the right part of the equation, the left side of the equation is going to be the same as before. We have a linear equation with constant coefficients. So nth derivative of the function y plus constant a1 times n minus first derivative of y plus, and the last term is an times the function y equal to, now instead of equal to 0, we consider this equal to some function, non-zero function b of t. So to find solutions, first we consider the corresponding homogeneous equation. So instead of taking this function b of t on the right side, we take 0 to obtain. So we take the same coefficients, a1 up to an, but on the left side, on the right side, instead of the function b, we take 0, so that we have a homogeneous equation. Now, from before, we know that this equation has n independent solutions. Y1 up to yn. Now, the general solution of this equation denoted by, we are going to denote it by y sub h for homogeneous. So the general solution of the homogeneous equation, c1 times y1 plus up to cn times yn. Here c1, c2, cn, real numbers, constants. Okay, so we consider the corresponding homogeneous equation. We find its independent solutions as we did in the previous lectures, and write the general solution. We call it y sub h. Then the general solution of the non-homogeneous equation, of the original non-homogeneous equation, maybe let's give this equation a name, dagger. So general solution of the non-homogeneous equation dagger is we take the general solution of the homogeneous equation, plus we have another part we call y sub p. P is for particular, where y sub p is a particular solution of a non-homogeneous equation. Okay, so it might look not logical because this is what we are trying to solve the non-homogeneous equation. If we are able to solve the equation to find this particular solution yp, why go through all these details of finding the homogeneous solution of the homogeneous equation and then the particular solution? Okay, you will see when we consider examples, in order to find this particular solution, if you remember, we did the same thing for the systems, linear systems. First, we solved the homogeneous equation to find this y sub h, and then to find this particular solution, we used the method of a variation of parameters. In order to use the method of variation of parameters, you need those independent solutions, y1 through yn, of the homogeneous equation. And then the method of variation of parameters gives you also the particular solution, yp. But for higher order differential equations, when you have just one equation, the equation dagger here, there is another more simple method of finding this particular solution. But as you will see in the examples, this method only gives us one particular solution, not all the solutions, just one particular solution. So to find all the solutions, we need this general solution, which we called y sub h, of the corresponding homogeneous system. So we do need the two parts, and I'm hoping that when we do examples, it will become more clear why we do need them. Okay, so this is the general way of solving non-homogeneous equations. First, find the solution of the corresponding homogeneous equation, and then using some method, find this particular solution and combine them to get your general solution. Now, in order to use the method of variation of parameters, we can use that method if the function b of t on the right side of your equation is a linear combination of the functions. So to use this method of undetermined coefficients, we need the function b of t to be of a particular form. And that form is a linear combination of the functions. In our list, we have three types of functions. Powers of t multiplied by exponential function. Powers of t times exponential function times cosine function. Powers of t exponential times the sine function. Here, k is a natural number. So it may be 0, maybe no powers of t appear. T to the 0 is 1, remember, or t squared, t cubed, and so on. Lambda and b, real numbers. They can be any real numbers. They don't have to be integers. They come from the solutions of these numbers, come from the solutions of the characteristic equation, if you remember. Okay, so if, all right, my sentence is not finished. So if the function on the right side is a linear combination of functions from this list, of course, it doesn't mean just 3 functions. You see, for different values of k, you get, even if you have the value for lambda and the number b, different values of k gives you different functions. So say lambda equals, I don't know, 2, and say b equals 3, you still have, okay, so first of all, you have e to the 2t. So e to the 2t cosine of 3t, e to the 2t sine of 3t. But then you also consider t times all of this. And then t squared, t cubed, and so on. So you see, even if you have the value for lambda and the number b, different values for k gives you an infinite list. Of course, we are not going to consider the infinite list. You will see how to limit the values of k. So if the function b of t is a linear combination of functions of this form, then to find yp, we guess the form as a linear combination. To find yp, we guess the form of yp, the form of yp as a special linear combination of functions from the above list. This method, okay, why is the method called method of undetermined coefficients? Because we are guessing, we guess the form of yp as a linear combination. So in the linear combination, we are going to have some coefficients for these functions in this list. So those coefficients, we find the coefficients in this linear combination by plugging the form of yp into the equation. We have the equation, we guess the form of this particular solution. Since it has to be a solution of the equation, we take that form that we guessed and we plug it into the equation, and we find the coefficients. That's why it's called the method of undetermined coefficients. Because first we take some coefficients which are to be determined. So in the beginning, they are not determined. So that's why it's called the method of undetermined coefficients. I think it will be clear. It is hard to explain this method in general lines. It will become more clear when you consider different examples. Okay, so now I'm going to consider some examples. Okay, so find all solutions of the differential equation as second derivative of y minus y equal to 6 times e to the 3t. So we have non-homogeneous linear equation with constant coefficients. All right, so first consider the corresponding homogeneous equation. Second derivative of y minus y equal to 0. So instead of considering the function 6 times e to the 3t on the right side, we take it to be 0. Okay, so we need to find a general solution of this equation. We already know what to do. We write the characteristic equation, lambda squared minus 1 equal to 0. So we have lambda equals plus or minus 1. So the first solution is e to the t. The second one is e to the minus t. So the general solution of the homogeneous equation, y sub h, c1 times e to the t plus c2 times e to the minus t. This part we do with the methods we learned in the previous sections. C1, C2, any real number. Okay, now to find a particular solution, look at the function b of t, which is 6 times e to the 3t. So in the list, remember the list, let me remind you. Okay, this is our list. So in our specific examples, we only have the exponential function. Okay. Oops, I'm sorry. Yes. In this particular example, the function b of t consists of just one term, and in that term we have the exponential function. No powers of t, no sine and cosine. So what do we guess to be the general form of the particular solution? So we guess that this particular solution is some multiple of e to the 3t. We don't know this multiple. This coefficient a is the coefficient we need to determine. Y, just the exponential function, because in b of t we have just the exponential function, and all derivatives of e to the 3t is a multiple of e to the 3t again. So the function b of t is a multiple of e to the 3t. And when you take derivatives, because in our equation, remember, we are going to plug this function into our equation. In our equation, on the left side, we have the second derivative and the function itself. But all the derivatives, the first derivative and the second derivative of e to the 3t is again just a multiple of e to the 3t again. So the first derivative is 3 times e to the 3t, second derivative is 9 times e to the 3t. So that's why we guess the general form of the particular solution to be some constant a times e to the 3t. So now plug yp into our equation, second derivative of y minus y equals 6 e to the 3t, to find the coefficient a. Okay, so let me write this again. Yp is a times e to the 3t. So when you take its derivative, it is 3a e to the 3t. A is just the constant. So the second derivative, 9a e to the 3t. So remember the equation. So we are plugging in this particular solution. Second derivative minus the function itself equals 6 e to the 3t. So the second derivative is 9a e to the 3t minus the function is a e to the 3t. It should be equal to 6 e to the 3t. So 9a minus a, 8a e to the 3t should be equal to 6 e to the 3t. So the number a should be 6 over 8, or 3/2. So our particular solution is 3/2 e to the 3t. Okay, so this is just one solution of the equation, but there are, so the idea is this: once you find this particular solution, to this solution you can add any solution of the homogeneous equation, because when you take then your general solution is just yh plus yp. Yp, we find it to be a solution of the original equation. Now, when you add a solution of the homogeneous equation, when we plug this into the equation, this part gives 0, and this part gives the function 6 e to the 3t. So when you take the sum gives you 6 e to the 3t, which is what you want. So your general solution then, yh, which is c1 times e to the t plus c2 times e to the minus t, plus the particular solution, 3/2 e to the 3t. Okay. So you see to find, okay, C1, C2, again, any real numbers. So to find this general solution, we do need the solution of the homogeneous equation, because homogeneous equation gives you 0, and then you add a particular solution to obtain 6 e to the 3t, and in this case, you obtain the general solution of your non-homogeneous equation. I hope that what we are doing is clear, but let me go over it again. So first, you consider the homogeneous equation. You write the general solution of your homogeneous equation. Then you guess the form of your particular solution and plug it into the equation to find your coefficient A. There may be more than one coefficient. I will do more examples, and combine the two solutions to obtain your general solution. So in this method, the only problem, not the problem, but the method lies in the step of guessing this form of the particular solution. That's where the method comes in. And now I am going to consider more examples to show you how to guess this form in different cases. So now, again, the question is to solve, meaning find all solutions. Second derivative of y minus plus 3 times the first derivative plus 2 times y equals cosine t. Again, first the homogeneous equation, y double prime minus plus 3y prime plus 2y equal to 0. So we write the characteristic equation, lambda squared plus 3 lambda plus 2 equal to 0. So we solve this. We can factor this out as lambda plus 1, lambda plus 2. So we get the solutions minus 1 and minus 2. So the general solution of the homogeneous equation, C1 times e to the minus t plus C2 times e to the minus 2t. Now, the function b of t is cosine t. Now, when you take the derivatives of the cosine function, you get the sine function, and the derivative of sine is cosine. So derivatives are multiples of cosine t and sine t. Cosine t, then the first derivative is sine t, second derivative is cosine t again. Cosine t is the function. The first derivative is minus sine t, second derivative is minus cosine t, third derivative is sine t, and so on. Some multiple of cosine t and sine t. So we guess the form of the particular solution to be some coefficient a times cosine t plus another coefficient b times sine t. Since in the derivatives we also obtain sine t, we guess the general form to be a combination of cosine and sine. There is no exponentials, no powers of t in this case, again. So we have just a combination of cosine and sine. And then now we plug it into